So I believe we are on air. So hello, dear colleagues. I'm glad to start our science talks uh, in Ukrainian Scientific and Educational IT Society. So today we'll talk about, in my opinion, extremely important and relevant topic in Ukrainian context, what covers social influence operations and the role of computer science in it. And before I will introduce our today's speaker, I want to remind you several technical issues. So if you want to ask questions, you're welcome to ask them in Q&A section and also in the comments under the live stream. And yeah, I will say them out loud. Yeah, and if you want to ask a question in Zoom with your voice, please raise your hand. So, and I'm glad to introduce our today's speaker, V.S. Subrahmanian, Walter Murphy Professor of Computer Science at the McCormick School of Engineering from Northwestern University, and Buffett Faculty Fellow at the Northwestern Roberta Buffett Institute for Global Affairs, also head of Northwestern Security and AI Lab. Yeah, and actually, VS visited Ukraine in 2023. So I believe you understand the context of Ukraine more than most of our speakers in the platform. So I don't want to steal your time anymore. The floor is yours.
Thank you, Dimitro. I will share my slides. Just please give me a moment. Great. I hope everyone can see my slides and that you can hear me okay. So today's talk is about the past, present, and future of social influence operations, but I'm going to mainly talk about the future. And first of all, let me express my solidarity with our friends in Ukraine, all of you. Slava Ukraine. So the work I'm talking about today is primarily going to be a paper that was published in the World Wide Web Conference in the end of April this year. It's joint work with 3 of my postdocs and a few other students. And one of them, Valerio Lagata, is actually here with me in the room as I'm giving this talk. He was one of the principal authors of this paper and much of this work. So as you all know, in Ukraine, better than perhaps almost anywhere else in the world today, influence operations, covert influence operations, are being carried out through things that we call bot farms, which are networks of accounts that have been compromised on some social platform or created from scratch by some malicious entity, such as, in this case, entities working for the Russian government. Based on the things we've observed in the wild over the last few years, we're not seeing huge differences in the ways in which these bot farm accounts are being run compared to what was done in the 2016 US election, the 2020 US election, the 2017 and subsequent French elections, and so forth. There are some differences, of course, which is that in the last few years, large language models and deepfakes have become increasingly important. And obviously, these are being used to achieve influence and scale. And another thing is that in the old influence operations, accounts were created, they would exert influence for a short while, and then they would disappear. And in contrast, what we've seen in the last few years is that fake accounts have been embedded within social channels for much longer than in the past. We expect the way these algorithms operate in exerting social influence to change a lot in the coming years. And, I would invite you to scan this QR code and answer these 3 questions. This is, when I give this talk with a live audience in person, it's easy for me to ask people to raise their hands. Today, I asked my postdoc Valerio to create a poll online with this QR code. And so there are 3 questions which I'll mention while you answer these questions for me. So when an account is positive about a topic, who is more positive about it? Bots or humans? So for example, when somebody says, I like beef, that's positive. But somebody who says, I really, really love beef is being much more positive. So that's what I mean. When somebody's positive, who's more positive? Bots or humans? Who disagrees more with people they are socially connected to immediately? Bots or humans? So in other words, if an account is present in a network and it has some followers of all people they follow, who disagrees more with those followers or followees, bots or humans? And then in terms of changes in opinion, who changes their opinion more often over time? So if you look at an account over a period of time, or a set of accounts over a period of time, say a week or a month, who changes their opinion on the same topic more frequently, humans or bots? So please take a look at this QR code and see if you can answer these 3 questions. And Valerio is showing me the answers so far. So interestingly here, for the first question, who is more positive when they are positive? The answer is bots in about 2/3 of the cases. For the second question, which is who disagrees more with others they are socially connected to, bots or humans? Again, it's bots, with about 70% people saying bots. And in the case of the third question, who disagrees more with others they are socially connected to, bots or humans? Again, the answer is mostly bots, 75%. And so those are the responses we're seeing. And these numbers are changing as I speak. But let me sort of tell you the results of the study that we did almost 10 years ago, where we looked at 10 months of data on Twitter in the context of the Indian election of 2014. And in that study, we asked the same questions. And interestingly, the answers that we observed were just the opposite of what your responses were. I don't remember what the sample size was in the responses we got, how many people responded to these questions, but the answer was overwhelmingly humans as the answer to all 3 questions. So when humans are positive about a topic, they tend to be more positive. When humans tend to disagree more with those they're socially connected to, and humans seem to change their opinions more often. So again, there's no right or wrong answer to these questions, but I was just curious to get some opinions from all of you on these things. So let's take a look today about how bot detection is done. As you all know, the social platforms, the Twitters and the Facebooks and the YouTubes of the world, Instagrams, TikToks, they're all doing a lot of work on identifying bots. And in fact, when you look at these platforms, most bots are detected well before any user ever sees them. They're detected and blocked. This is typically done by using learned machine learning classifiers. So over time, the platforms have created machine learning classifiers to distinguish between bot accounts and real accounts, just as they've done the same to distinguish between true information and misinformation or disinformation. So they learn a machine learning classifier. However, if you're the bad guy running an influence campaign and you want to evade the controls of a social platform, there are many ways you could try to do this. The first thing to note is that machine learning classifiers try to learn a model. As soon as we say learn a model, it means that they assume the existence of a single model to separate real accounts from bot accounts. From the point of view of the adversary, the person running the covert social influence operation, the person controlling the bot farm, his goal is to prevent the adversary from learning a good model that distinguishes between real and bot accounts. And one way to do this is for that bad guy, the adversary, to continuously change the model that he's using to create bots and to deploy those bots in the pursuit of whatever objectives he has. So to give you an example, you see here a timeline on the x-axis. The y-axis doesn't really matter, but for some period of time, at time 0, at the bottom left of this coordinate plane, there is the influence operation has started, and the attacker is running his model, and the defender is running his model. For now, you can assume the defender is a big social platform. At some point, the attacker decides to update his attack model. And then the defender continues with his defense model. And the attacker and defender, they're not necessarily playing one move at a time. They're doing their thing as frequently as they want and without necessarily worrying about the order. And at some future point in time, the attacker updates his model again. And at another point in time, he updates his model again. So what this means is that the attacker, to launch a successful attack, can continuously learn from the defense. Learn by observing what the defender is doing, just as the defender is observing the attacker and trying to figure out what his attack model is. So again, from the smart attacker's perspective, learning how to evade the attacker's defense can be done automatically. And that's what we're going to show in this paper. So rather than waiting for a certain amount of time to change the attack model, what we're going to claim in this paper, which was published in the World Wide Web Conference 3 months ago, 2.5 months ago, we can show how to do this automatically. And that's what I'm going to talk about today. So for this, we propose something called reinforcement learning-based covert social influence operations, RLCSIO algorithm, or in plain English, I'm going to call it the bot farm algorithm because that's more pronounceable. I'm going to make some assumptions. As we do in science, all work has assumptions. And we assume that the attacker has numerous accounts that he or she controls on the social platform. So we're looking at one social platform, and we're going to assume the attacker controls a certain number of accounts. In today's talk, I'm not going to worry about how those accounts have been controlled, how the attacker got control. We can discuss this later if you wish. But he could have created the accounts, they could have hacked accounts that exist, and more. We also make some assumptions about the actions the attackers can take, and examples of the kinds of actions that the attacker can take is to create posts, and in particular, decide on the content and the sentiments in a post. I'm not that worried about generating the content of the post or the sentiments in the post because we can do this automatically nowadays with LLMs as long as we know what we want to express in the post. What is the message and sentiment we want to convey in the post? As long as we can express that, we can use LLMs to do this automatically. Another attack option is the attacker has a number of accounts they control. They can decide which bot account that they control should post a piece of content. They can decide which accounts on the platform should be followed or unfollowed by their bots. And they can decide which posts made by other accounts to like or not. There are, of course, many other actions that can be taken, but these are what we considered in the current work. And obviously, the same algorithm, RLCSIO, can be adapted to more actions as well. For now, we assume the defender has one single action, and that is, at any point in time, the defender can decide to block an account. So it can say, oh, here are 100 accounts. I'm going to block accounts 1, 17, and 26. And the defender can choose to block a certain number of accounts anytime he or she decides to do something. in this work, I'm going to talk about the offense side. Over time, the idea is that our algorithm, the RLCSIO algorithm, should learn a model of the defender's black box classifier. So what do I mean by a black box classifier? In the real world, we don't know what algorithm a major social platform is using to detect bots. We don't know what features they're using to detect bots. So we assume that the adversary doesn't know that either. And that's perhaps the most realistic thing. The guy running these bots does not know what the algorithm used by the defender is, and so he's got to figure out how to learn it dynamically. Our algorithm has to balance two competing objectives. If you've got an account that has been around, you control an account that has been around for a long time, that has its own followers, that has been engaged in the social community that it's part of for a while, losing that account is a cost to the attacker. So on the one hand, the covert social influence operator wants to minimize detection of fraudulent accounts, but on the other hand, he wants to maximize the spread of whatever influence that he wants to spread. So again, I have a few questions for you, and I'll reveal the answers to you in a few minutes later in the talk. But for now, some slightly different questions from those that I asked a minute back. And again, there's a different QR code this time to enable you to participate. And at the end of the talk, I'll ask Valerio to post a link in the chat with the results of these two surveys. So the first question is, do bots become top-tier influencers? That is, do they rise to become high-level influencers? So we are going to run experiments and talk about experiments in which people can say, I was influenced by this account. I was influenced by that account. So what types of accounts, bots or humans? What is the relationship between the level of activity that they have? Are more active humans or bot accounts more likely to be reported as being influential? So if you look at human accounts, if they are more active, are they more likely to be reported as influential? When I say more active, I mean in terms of posts, likes, other activity on the platform. If you're a random human on the platform, does greater interaction with bots correlate with a higher probability that you will change your stance or your position on the topic and sentiment pushed by the bot? So the bot is trying to move sentiment to be positive or negative on some topic. So if you interact more with a bot, are you more likely to change your stance on that topic? And then, do bots dynamically change their behavior over time to evade detection by the black box of the platform? So please take a look at these 4 questions. The QR code is at the top right of the screen. If you can answer that, again, as I said, at the end of the talk or earlier, Valerio will post in the chat the results. So let me say a little bit about the methodology that we use. We start with a social network, which is a graph consisting of some vertices. I hope you can see my cursor on the screen. And these are the gray nodes, circular nodes you see here, and some edges. An edge is typically from a follower node to a node that it follows. So in this example, the edge from U1 to U2 indicates that node U1, account U1, is following user U2. In addition, we can label the edges with weights in many ways. So to give you an example, the weight could be the number of interactions between U1 and U2, such as the number of likes, the number of things that U2 posted that U1 liked, for example, or the number of things that U2 posted that U1 reshared or retweeted, and so forth, or some combination. What we want is that the greater this weight is, the greater the interaction between those two accounts. Now, you can define this graph in many other ways as well. This is what we did in our paper, but you can see that the same techniques that we articulate in this talk for the RLCSIO algorithm will operate and will still apply. Now, a covert social influence operator CSIO agent 1 is running an influence operation. The goal of this influence operation is to influence opinion on some subject or some topic, which we call sub-CSIO, and to spread opinion with some polarity, positive or negative. Now, in this paper, I'm going to assume that a positive polarity is always being spread. If it's a negative polarity, it'll apply in the same way. To achieve this goal of spreading polarity to be positive towards some topic, the CSIO agent, think of the CSIO agent as a centralized agent, controls a number of accounts shown in red in this slide. So U3, U9, and U11 are 3 nodes controlled by this specific CSIO agent. Now, in the real world, of course, there are lots of different influence operations occurring on social platforms at the same time. And these may be occurring independently. They may even be on the same topic, so not completely independent, but they're run independently. So organizations A and organizations B may both simultaneously want to influence opinion on a certain political topic or a certain election, for example. And so we show the fact that there are multiple operations happening by highlighting in this picture a second CSIO agent that's running a second covert social influence operation shown in purple. And for that particular agent is controlling U5 and U10. Again, this is obviously a very small network. Each account has some attributes, and the attributes are the following. The role of the account, it's either a bot account or a CSIO controlled account. Now, let's put ourselves in the shoes of the CSIO agent that is controlling the red accounts. In this case, this guy running the red covert social influence operations knows that U3 and U9 and U11 are bots. Even though U5 and U10 are bots, the red agent does not know that because those are being run by some other agent. Okay, so please keep that in mind. Likewise, the purple agent, which is running U5 and U10, does not know the identities that U3, U9, and U11 are bots because these are independently run operations. So the role of an account from the point of view of a specific agent is simply, am I controlling this? Is it one of my controlled bots or not? Centrality of an account can be measured in many ways. Eigenvector centrality, degree centrality, etc. Another example is PageRank. Polarity is the polarity of this account towards whatever subject and position is being pushed by the CSIO. And as we're always pushing things towards positive, this is either positive or negative. Blocked. Is the account blocked or not? And active is a numeric metric which says how much activity has this account engaged in from the beginning. And when I say the beginning, it's the beginning of some period of time of study. We're assuming that the covert social influence operation can track the public actions of the bots that it controls, which seems reasonable, as well as the accounts following it, which also seems reasonable and can be easily done in the real world. Here's an example of what these 5 attributes might look like for U2. So the CSIO agent running the red campaign might say this is a normal account because I'm not controlling this. Its centrality is such and such. It's positive towards whatever opinion the red campaign is pushing. It's not been blocked yet, and it's done 10 things, such as posts, likes, etc. In the case of CSIO accounts, bot accounts that it's controlling, which are not blocked, those unblocked accounts can do various things. They can choose, if U is that account, it can choose to follow an account U prime. It can choose to post a post on topic, on a subject, not necessarily the one that it's trying to influence. With some polarity, it can decide to like a post by another account, or it can choose to do nothing. Please note that choosing to do nothing is an explicit action. It's a choice made by the agent that this account will do nothing. Please also note that in this framework, we're assuming the CSIO agent is a centralized agent. So it's making the decisions on what the different it's like a puppet master. It says, I have this account, this account, this account. I'm going to make this account do this thing, this account do this thing, and this account do something else. So at any point in time, the CSIO agent controls some number of accounts, K accounts, and it must decide which of these actions to take for each account that it controls that has not been blocked already. Now, some accounts could have been relatively silent in the sense that they have not been doing anything and not spreading influence because the CSIO agent has not used it to spread influence yet. In such cases, the CSIO agent can choose to activate this account and make it start spreading and participating actively in whatever influence it wants to spread. What does the social platform do? We're assuming the social platform operates a bot detector. Our agents running the CSIO agent has no knowledge of the details of the bot detector. So it can observe what happens to accounts on the platform that it can see, but not what the details of the bot detector are. So it has no knowledge of any of that. The social platform is assumed to block an account if the probability of its being a bot is greater than some threshold according to the bot detector. And the bot detector screens all accounts on the platform at periodic intervals, and that periodicity, how frequently that's done, is also not known to the CSIO agent. In our experiments, we used a bot detector from a few years back, which had very good performance, reportedly, on 2 data sets, F1 score of 90% on the social honeypot data set, and a 77% F1 on Twibot, which is also considered a well-known data set. So state. The CSIO agent is reasoning about state. And the state is represented with 2 things. One is the adjacency matrix of the social graph at time t. Notice that accounts are following and unfollowing other accounts frequently. So the adjacency matrix is always changing. That's why J sub t is the adjacency matrix, and it's telling us which accounts are following which other accounts at any given point in time. In addition, there's the feature matrix for each account. For each account, such as U1 and U2 and so forth, shown in this table, there's a 5-dimensional feature vector consisting of the role of that account. U1 is a bot for the campaign in whose, we're pretending we are one of the social influence campaigns. So when we're running this is one of our bots, whereas U2 is a normal account, though in reality, it could be a bot account for some unknown campaign. We can measure the centrality of U1. We know whether, or any of these accounts, we can look at the polarity of the posts and decide whether that account is positive or negative or neutral on the topic of interest to our social media campaign. So even though there may be these user accounts may have positive or negative opinions on lots of things, the polarity field is about the topic of interest to the CSIO, the covert social influence campaign that is being operated in this example by the person whose shoes we are putting ourselves in. This tells us whether the account has been blocked, and this says something about the level of activity of this account, the number of actions performed by the account during a given period of time. We want our covert social influence operations to dynamically learn as things evolve. And to do this, we do this through a reward function. The reward function is complicated and has 4 components, and I'm going to have one slide on each component. The first is if we are running a covert social influence operation, we want to influence humans, not bots. So we want to incentivize our agent to interact with other accounts that it thinks are humans. And we capture this through a reward function 1. This is the first component of the reward function. That's why this is R1. You look at so this looks at the reward for agent I. So imagine user UI is a bot controlled by the covert social influence operator or the bot form. And the reward for bot I or bot account UI is to look at the neighbors of UI, that is the followers, see whether they are humans are not. So role equal to 1 means account uj, which is a follower of ui, is human, and at time t. And then see what the corresponding number was at time t minus 1. So at time t, let's say there are 40 followers of this particular bot u1, and at the previous time point, there were 30. In that case, in the intervening 1 unit of time, this account gained 40, which is this term here, minus 30, which is 10. It gained 10 new humans who are following it. That should get a reward, and that's what this R1 function tries to capture. Now, there's a termination reward, which is our sub-reward R2 function, which says, oh, if all the accounts have adopted the same position that we want everybody to adopt, then we're going to give this block mega reward H to the bot account U1. And that's just a flat fixed, think of it as a fixed reward for getting everybody on board. That's an unlikely reward to ever be achieved in the real world, but we just wanted it in there. A more likely reward is what we call the infection reward. And this is the reward if the neighbors of account I achieve the desired polarity. Now, this is reward function R3, and it says bot UI, the ith bot, gains a reward which looks at the neighbors, the followers of UI, bot account I, and it says, let's look at a follower. Look at the weight of the interactions between the follower and the account UI, and look at the influence of UI at time t, which is computed from the graph at time t. The greater the influence of UI, I multiplied by this to get an expected influence or a weighted influence of UI at time t on all its followers. That's what this expression here says. This expression, the minus expression here, is the same as this, except applied to t minus 1. So the difference between this summation here and this summation here is giving us the weighted influence improvement from time t minus 1 to time t. And obviously, if the bot u sub I gain increased weighted influence at time t compared to time t minus 1, there should be a reward for that. And then last but not least, the bot form or the covert social influence operator should pay a penalty if one of its bot accounts is detected and blocked by the platform. So that's, we assign a fixed fee, so to speak, a fixed price or cost if an account is blocked of minus k. So this is a negative expression. And if 3 accounts are blocked at time t, then it's minus k times 3 minus 3k, where k is some constant. By the way, I should say that these 4 rewards can be defined in other ways as well, but these all are reasonable ways of defining it. So we don't claim these are the only ways to do it, but these are reasonable ways to do it. The total reward for gained by bot I at time t is a linear combination of these 4 rewards. You get rewards or positive rewards for the first 3 and a negative reward for being blocked. So that's the reward function that's used by the covert social influence operator, who's then operating a Markov decision process to figure out what to do. The Markov decision process has 5 components, as is usual. The state space, the action space, I've told you what the states look like. I've told you what the actions look like. I've told you what the reward function looks like. We assume the existence of a discount factor gamma, which balances immediate rewards from potential future rewards. And so as rewards become more and more distant in the future, the discount factor has a bigger and bigger impact, diminishing rewards 100 time units from now compared to rewards 2 time units from now. And this is a common strategy in reinforcement learning. There's also a transition probability function, which is the probability of transition from a state to another state when an action is performed. And we sample this through extensive experimentation. So the goal of the covert social influence operator is to find a policy that maximizes the expected cumulative reward over time. And this expression here, the E followed by this big expression, is capturing this expected cumulative reward. Obviously, we cannot do the summation all the way up to infinity. So we set the summation to max out at t equal to 200 in our experiments. The reasoning architecture used by the CSIO is a graph convolutional network, and that's used to encode the state of the Markov decision process. So as you can see here, here's the original graph. The red nodes are the CSIO nodes. The blue nodes are what are, at least from the perspective of the red CSIO agent, normal users, even though, as I said earlier, they could be bots operated by other CSIO operators independently. So the input graph is basically convolved by the graph convolutional network to produce node and embeddings for each node, that is for each user. And those are then, so these node embeddings capture both the properties of the nodes in the graph as well as the relationships the graph has, that is the topological structure of the graph. To compute the policy, we leverage an actor-critic network and a synchronized version of the proximal PPO algorithm to learn the proximal policy algorithm to learn the best policy for the CSIO accounts. The actor network is a fully connected neural network that basically selects actions by the CSIO accounts, that is the bots. It says, okay, here's the next action to be taken by a bot, and it returns a probability density function on what that next action should be. At training time, the bot samples the action based on the probability distribution to improve exploration or learning. But at operations time, the bot performs the action with the highest probability to gain the highest expected reward. The critic network is a fully connected neural network which tries to estimate the value function. That is the value or the payoffs or the rewards for the CSIO accounts of the actual state. And it concatenates the node embeddings and estimates the reward achieved by that bot. And it does this for each and every bot. So what does the training process of our RL-CSIO agent look like? We trained it with agents simulating human players with some statistics from the literature. And I'll say more about that. The initial network was randomly created, and we trained the RL-CSIO agent for 10,000 episodes, each with a max of 200 steps, as I showed earlier. The human agents were simulated via various distributions, and here's one example. Now, in the real world, we know that most humans on platforms are not on the platform all the time. Some people may be, but most people are not. So according to third-party studies, the average US user spends 3 hours daily on social platforms. So we assumed a user would do nothing for about 80% of the time. And this is one example of how we use third-party studies to estimate how humans would behave. In terms of other account actions, so this is the no-op action. In terms of other account actions, we assumed all other actions are equally probable, such as deciding to post, such as deciding to like, such as deciding to reshare, etc. And we updated the polarity each human user's polarity on a topic is randomly initialized. And in the training, we updated the polarity by doing a linear combination of the polarity of the last action taken and the user's polarity at the previous point in time. So the eta expression here, weight coefficient, is expressing the trade-off between the polarity of the last action taken by the account at time t and the polarity overall of that particular account u sub I at time t minus 1. In this case, please note that these u sub i's are human accounts. For the post action, polarity is obtained from the sentiment in the post, and for follow-like actions, we look at what is being followed, who's being followed, and their polarity, what post is being liked, and the polarity of that, and that's using a third-party engine called Vader to do sentiment analysis. As I said earlier, we use proximal policy optimization, PPO, with a max of 200 iterations. Okay, so we then ran, so that was for training. And then we said, okay, how does all this work? So we ran experiments with a total of 225 subjects from the US over a 5-day period. When participants engaged in the experiment, they engaged for at least 30 minutes per day. Obviously, we could track that. And they also filled out a survey before the experiment started and at the end of each day of participation. And this survey expressed their attitudes, as well as they told us which accounts changed their attitudes, which accounts influenced them. We ran 4 concurrent CSIO operations. Each operation was on a different topic. For example, one was the statement, the US government did enough to combat COVID-19. Another was a 2% wealth tax on people with more than a certain number of assets should be approved. The third proposition said Medicare for all who want it is a good thing. And a fourth said food containing genetically modified organisms is safe and healthy to eat. By the way, we don't personally take a position on any of these statements. These are just statements which are where we know there are lots of differences in opinion amongst ordinary people. We ran the CSIO agents, one for each of these 4 CSIO operations. We ran them so that they were independent of each other, and we used the bot detector that I told you about earlier. Each CSIO agent operated 20 accounts. So in total, there were 80 CSIO accounts plus the 225 human subjects for a total of 305 accounts or nodes in our graph. The reason we did this is because we cannot run covert social influence operations on real-world platforms in an ethical way. And there are many reasons for this. One is it would be a violation of terms of use of the platforms to do so. Another would be that there would be a lack of informed consent from the participants, etc. We therefore used a platform called Dartpost that one of my former students had developed to run these experiments. So Dartpost is a platform that allows you to run such experiments. It allows you to mimic the behavior of the social platform, so you can run interventions by the platform. It allows you to recruit subjects to participate in experiments with informed consent, so the IRB requirements are satisfied. And it enables you to measure everything. So Dartpost, for example, even measures screen time. How long is a post shown on the screen to a particular user, etc. So we initially started with a random follower-followee network with our 305 nodes using a long tail distribution, which is typical of the follower-followee networks from the literature. Most users had 3 to 6 followers with an average of 5 when we started out. And each account had a realistic profile with a history of past posts already put in here, which was sampled from a previous paper. These are some screenshots of what the Dartpost system looks like. Yeah, so this was a paper that I led a few years back. So now let's go back to the questions that I'd asked you to look at, and I'm asking Valerio to show me the results. So for the first question, do bots become top-tier influencers? Can you bring it a little closer? About 76% of people said yes. Are accounts which are more active more likely to be reported as influential? About 80% said yes. On the question, does greater interaction with bots correlate with a higher probability of stance change? About 61% said yes. And for the last question, do bots dynamically change their behavior over time? About 73% said yes. Okay, so the answer to all of the questions was basically yes. And I'll give you the answers in a few minutes, the answers we found. But you're all mostly right. But on one question, not so. So I'll let you all think about what that question might be. So, okay, I guess the answer is on this slide. Okay, so the first question was, do bots become top-tier influencers? And the answer is really no. So bots try to influence humans, but don't try to become top-tier influencers. We defined in our paper, as I said, the notion of an influence report. So when we do the daily surveys, a user can say, oh, I found this account to have influenced me a lot. So if I was one of the users in the study, I could say, oh, account 26 and account 67 influenced me today. So the question we asked is, how many bots received influence reports? And that you see in the orange part on the right side of the screen of this chart. And then how many humans received influence reports? And you see that in green on the left side of this chart on the left. The median number of influence reports was the same, 3 for both humans and bots. But what you see here is that in terms of the number of influence reports for humans, there's a very long tail. You can see this tail stretching all the way to the top. There were some humans who received more than 20 influential reports during the study. So in contrast, no bot received more than 8 influence reports here. And we can show that the Brown-Forsyth test, which is a statistical test which has very few assumptions compared to other statistical tests, confirms the difference between both groups. Humans may end up becoming top-tier influencers, but bots generally not. So that's a difference between what you all thought. I should say that a similar result was present in my 2014 paper on the 10 months of data on the Indian election from that year. And we don't know why, because we didn't interview these subjects specifically. We don't know why this is the case, why bots seem to be less influential. And the reason I expect is that the bot creators do not want the bots to become so influential that they are noticeable and subjected to scrutiny by humans, and thus perhaps revealed as being bots. Perhaps, we don't know for sure. What about human activity and influence? So here, the question is it humans or bots who tend to be more influential as they increase their activity? In this picture, on the x-axis, you see the number of actions taken. And on the y-axis, the number of reports of being influential. And the orange line shows so each circle is either a human account or a bot account who is reported as being influential. And what you see is a slight increasing trend for both the bot accounts, the CSIO accounts in orange, and the human accounts in green. But the human accounts have a much bigger slope. The green line has a much bigger slope. So what we did is to do both the Spearman correlation to understand the relationship between the number of influence reports, the number of reports of being influential received by bots versus humans on the one hand, versus the number of actions they took. In the case of humans, that correlation is 0.5, but only 0.1 for bots, much lower. We also did a linear regression analysis, and the R squared for humans is 0.41 with a p-value of a very small p-value, something on the order of 10 to the power of -7, whereas in the case of bots, the regression is inconclusive. So the takeaway message for us is that greater activity by humans implies greater influence, but that is not necessarily the case for bots. We don't have evidence that that's the case for bots. Again, this might be because bots want to stay below the radar. They want to push influence at a very slow level, but to have lots of bots to do it. Again, that's just a hypothesis. We can't be sure about that. Now, what about humans who in their survey responses say, oh, we were influenced by some other humans? Did they change their stance on the topic that's being pushed by those particular accounts? What we see in this chart on the left is the percentage of users who reported stance change compared to, for each of the 4 topics. We can see that about 40% of users change their stance, increase their stance. Remember that all our bots are pushing opinion towards the topic, to be positive towards the topic. There's no loss of generality in that again. But what you see here is that 40% of the accounts increased their stance towards COVID-19, 60% towards Medicare, and so forth. And this is those users who reported influence, by the way. So humans who said they were influenced, 40% of them increased their stance towards COVID-19, 60% towards Medicare, 50% approximately towards wealth tax, and so forth. So the Pearson correlation coefficients, again, were about between 0.22 and 0.37. We did a secondary comparison where we said, what is the probability of a user changing his stance on a topic? And for each of these 4 topics, it was about 25%. But when we look at the conditional probability, the probability of increasing their stance towards a topic, given that they reported they were influenced, that probability went to over 40% for each of the 4 topics. So the takeaway here is that the probability of a stance change, a change of stance on a topic, goes up when the human reports being influenced by someone else, regardless of whether that someone else is bot or human. So then we said, oh, what about interaction of humans with bots versus humans? And the picture you see here shows the influence ratio of a user. The influence ratio of a user is the percentage of accounts that a user reports as being influential. I'm sorry. So if a user reported, say, 10 accounts as having influenced him on the topic in question, and 4 of them are bots, then the influence ratio for that user would be 40%. So you can think of it as the bot influence ratio as opposed to just influence ratio. And remember that all these bots are pushing influence only towards a stance increase. So what you see on the y-axis is the 2 groups, the users who increased their stance towards the topic and the users who did not. You can see that the means are different and that humans that increase their stance have a higher influence ratio, were more likely to have been influenced by bots. Interesting, right? That bots are influencing humans perhaps more. And so what the takeaway here is that bots can effectively drive humans towards the ideas they're pushing. And then we said, what about this trade-off between influence and discoverability? How successful were the bots in adapting their strategy to avoid detection? The dotted lines that you see in the 4 colors denote each of the 4 influence campaigns that were run, the blue for COVID-19, the orange for Medicare, green for tax increase, and GMO with the red triangles, the red line. And the dotted lines show the number of bots discovered on each day. What you can see, if you just look at the dotted lines, is a generally decreasing trend as the days of the experiments proceeded. And at the end of the campaign, so what this decreasing trend suggests is that over time, the bots learned how to evade detection. At the end of the campaign, there were 16, 15, about 14, 15 bots that were suspended in the 4 campaigns, but none of the CSIO campaigns had all 20 bots. And in fact, the black box bot detector's actual performance as our RL CSIO bots learned their strategy, the F1 score was only 0.535. If you remember, the F1 score of this black box detector in the experiments reported by the paper with no RL being used to evade them was 77% on the TWIBOT dataset and over 90% on another dataset. So this suggests that the bot evasion strategies learned by our CSIO bots has diminished that F1 score to 53.5%, which is a huge drop. So effectively, the RL CSIO bots that we designed are able to effectively evade detection. A little bit about exposure to bots. As a human is exposed to bots and the activities of bots more and more, does that human's ability to detect bots goes up? Now, here's something that's hopeful if you're a human who wants to stop bots in their tracks. Past studies on human ability to detect bots have generally found humans don't do a very good job. Our study shows a more nuanced result. It says, what is the relationship between greater exposure to bot activity and the ability to detect bots? And what you're seeing here is an increasing trend on the y-axis compared to exposure ratio. Exposure ratio of an account. So if you as an account or a user, the exposure ratio is the percentage of posts made by bots that the user sees to the total number of posts that the user sees. So an exposure ratio of 40% means that that account saw 40% of posts, 40% of the posts that that account saw were made by bots. What you see in this graph is that all three measures, precision shown in blue, recall shown in orange, and F1 score shown in green, all three increase as exposure to bots goes up. And it's quite significant. And you can see that with the linear regression analysis with the R squared, and the p-values that are reported here are all statistically significant. So humans get better at detecting bots the more they're exposed to posts by bots. And conversely, what this says is, if you're a bot and don't want to get detected, you want to make sure that the same human is not exposed to too many bot posts, but that might also reduce the probability of influencing that account. So that's the challenge for the bots and is also some hope for humans. And then here's this really interesting finding. Being perceived as a bot doesn't seem to hinder the ability to influence others. So humans are still being influenced even if they perceive an account to be a bot. That's really strange. So 20% of humans in our study report being influenced by at least one account that they also reported as a bot, okay? And so what you see here on the x-axis is the number of bot reports, and on the y-axis, the number of influential reports. And you see an increasing trend both for normal accounts in green and bot accounts in orange. I know I'm running low on time, so I'll just very quickly say that being perceived as a bot does not seem to hinder the ability to influence others either. So this is sort of an extension of this slide. And RL CSIO bots are basically able to shift humans' opinions in a given direction, even if those humans suspect that they might be bots. So coming back to the questions that I asked, most of you gave answers in the 70+% yes answers to all these questions. You were right on questions 2, 3, and 4, but not on question 1, where bots don't seek to become top-tier influencers in our study, as well as in the previous study I did 10 years back. So our paper doesn't report on what the smart defender should do, but one strategy that I just want to say a few words about is for the smart defender to dynamically update his own defense model periodically as well, so that the attacker cannot learn an accurate model of the defense. And so what used to be a human-in-the-loop process is now likely moving towards a fully automated cat and mouse game, and we expect this is what will happen in the coming years. So by the way, our paper can be accessed at this location online. I'm leaving the slide up for a minute, and you can also download data from our experiment at this website as well. I'll ask Valerio to post both these links in the chat as well, Valerio, while I continue. So I just want to say a few more words about a system that Valerio is not involved in, but one of my other postdocs, Marco Postiglione, and a fantastic team of researchers from my group here at Northwestern have been working on, and that is something called the Global Online Deepfake Detection System, or GODS. GODS was released, or not released, but made publicly available as a service to journalists on July 8th of last year. So over a year has gone by. Over 70 journalists, maybe more by now, have used GODS since then, and they include journalists from all over the world, including some major ones, such as CNN, Al Jazeera, New York Times, etc. And I'm just going to go over this quickly. In Ukraine, you've obviously seen a lot of deep fakes, but I'm going to play a couple of deep fakes. A couple of artifacts for you and ask you to tell me what you think. This is an artifact from an election in Mexico, which is a
Mira, eso me venía diciendo Barack porque la corrieron los frutos cafetaleros. ¿Cuántos cafetaleros crees que son entre Huatusco y Tototlán? Le contestó un panista que 100,000 y digo, te regalo más, te regalo más.
You may not know Spanish, and that's okay. I don't know Spanish either, and we still had to figure out whether this was real or fake. Our God's platform internally has a lot of tools to deal with foreign language content. And so I just want you to think about that. And I want you to think about this one as well.
Trust your own judgment. Do you really think you can make money with your stocks? Follow me and my student, Mr. Vinit. We will provide you with free stock diagnosis and investment plan customization and recommend stocks worth buying in the future stock market.
So this gentleman at the top of the screen who's speaking is Mukesh Ambani. Mukesh Ambani is India's wealthiest man and one of the richest men in the world, one of the richest people in the world. And he is the subject of frequent deep fakes. Again, you know, the reason I'm just saying is that this is not... so one reason, you know, so till the work we've done, almost all past work focuses on analyzing the artifact alone. So in other words, they just look at the audio clip or just look at the video clip as on the previous slide or this slide. But this isn't always smart. Why would you limit yourself to the audio clip or the video clip alone if, as in the case of these two people, very well-known public figures, one in Mexico, the other in India, and more globally as well, in the case of both these individuals, there's a lot of contextual information. For example, we know that there's been a history of Mukesh Ambani deep fakes, misrepresenting the videos as him, deep faking him to sell various kinds of scams. So obviously, Mr. Ambani is not doing that, but malicious actors are doing that. And why would we not use the fact that this has been deep fakes of him selling various kinds of scams have been created by actors in the past to inform our judgment about whether this is deep fake or not. So we developed a system called CAD, Context-Based Audio Deepfake Detector, and it automatically extracts relevant news, Reddit, Wikidata information about the subject of a audio clip, and we can show, compared to baselines, that various versions of CAD do improve performance dramatically in predicting whether an audio clip is a deepfake or not. Here are some multimodal posts, and I invite you to look at them. And I'm not doing a survey this time. I'm just asking you to consider, are these real or fakes? So I know, for example, that, you know, in Ukraine, you have some good football teams. This is a clip about a multimodal clip consisting of text and image. Think the kind of thing that somebody may post on a social platform. Here is a clip from Ireland. Here's a clip on a surprising interview with a former Russian central banker. And question for all of you is A a deep fake? Is B a deep fake? Is C a deep fake? Is D a deep fake? Now, you can ignore the user part because we blanked this out and just replaced this with some dummy stuff at the top. Now, it turns out that all these four are fakes. These were generated in our lab by Valerio and some of my other students and postdocs. And here's an example of another paper that I wrote with a couple of my students who are incredible and a colleague from Dartmouth College. And this is about generating engaging multimodal content. So if you look at this, this is pretty engaging, the posts on this. So this says, furious Bukayo Saka confronts referee after being denied a last gap penalty in Arsenal's draw with Bayern Munich. Unbelievable decision by Nyberg. Want to know more? Read the full story on Mirror Football. Blah, 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 blah. Okay, various hashtags, some emojis like here, etc. And these look pretty realistic, okay? But these are all fake, AI-generated content. When I say fake, I mean AI-generated content. But AI-generated content that can be for good or for bad, okay? So AI-generated content that's used to create a post that says the real thing may be okay if it's not lying or spreading disinformation. AI-generated content that, again, is honest and is used for advertising may also be good. So this, everybody likes pizza. So here's a prompt at the top of this panel which says Pizza Amore is a pizzeria that serves amazing pizza. Please generate a tweet talking about how the pizza is genuine Neapolitan thin crust pizza. Everything below the top text, which is the prompt, is generating this. And this is generated in a way that is intended to align the image and the text together, make the image attractive and the text attractive, so that an algorithm that predicts whether a classifier that predicts whether the multimodal content generated is engaging or not receives an engaging label. And this is done by training on a massive database of Instagram posts and using the number of likes to decide on whether something is considered engaging or not. If there are lots of likes, engaging; if not, not engaging. You can see that the text and the images, which are from 4 different areas of human endeavor, are quite attractive, at least to me, okay? And if I look at the pizza, this looks like a realistic pizza picture. This tweet looks pretty good. There's a picture of a slice of pizza, happy-looking guy or woman, I'm not sure. Nothing beats the taste of authentic Neapolitan thin crust pizza. So again, I want to emphasize, not necessarily good, not necessarily bad. So I'm just going to say a little bit that the use of context increases the F1 score of deepfake detection quite a lot. And this can also be used in order to look at content posted on social platforms, stuff we're doing right now. So with that, I'll stop. Here's some contact information for me. And again, feel free to ask questions. And hopefully, Valerio has posted material. Sorry, let me make this maximum size. Hopefully, Valerio has posted some of the links in the chat during the talk. So thank you very much.
Thank you. It was really interesting, at least for me. I believe for our listeners also. So I have several questions. We have several questions in comments under the live stream. So the first question I wanted to ask about agents. As I understood, agents were pre-trained in a simulated environment where human behavior was approximated. Yeah. So
Yes.
How closely does the simulated environment approximate real user interactions? And did you measure the distributional shift between the simulated and real behaviors?
Great question. We did not do that. And I'm going to take that as a suggestion for us. We have the data to measure that for sure, okay? But we didn't do that. As you know, when we submit a paper to a conference, we have a page limit, and we have to be very careful about fitting into the paper just the right things. In this case, we didn't actually do it. So we didn't make a conscious decision not to include it. We didn't do it, so it's a great suggestion.
Okay, great, thank you. We have several questions also. The first question is, how did you validate the reliability of self-reported inferences? Could there be biases introduced in self-perceptions?
So very good question. So, in most of the work on influence operations, there are no surveys, okay? So the fact that person A influenced person B is assumed based on some technical properties. Oops, sorry. Okay. And we didn't want to do that. So that's why we asked human subjects who influenced them. We did not have a good mechanism to determine whether it was biased or not. I don't think we actually have the data to make that judgment, but we can take a look. Yeah.
Thank you. Another question. What were the primary behavioral changes observed in bots during adaptation? Did you quantify these changes?
Yeah. So again, it's a good question. We've thought about doing that, but we've not done that yet. Again, we have the data. So part of what happened was this experiment over 5 days generated a lot of data. We've analyzed some of it, and we are continuing to analyze more of it. So as we paper that talks about adaptation. Yeah.
Great. So I had another question about the data actually, and the data from different platforms. Because what I observe, not actually from, I don't know, big data sets, just as a user of social media, that bots behave differently in, for example, Facebook, Telegram, and Twitter. So have you evaluated that? And does your model depends on the social media?
So very good question. I don't know if it's from you, Dimitro, or from one of the audience.
Yeah,
So
it's from me.
Okay, so it's a very good question. Your question is absolutely right, that bot behaviors we've seen in Facebook versus Twitter versus Telegram have been quite different. Let me say that, running one of these 5-day experiments is very challenging, okay, in many respects. One is we have to get the IRB permission. Another is when we recruit 225 subjects, as we did in this experiment, we have to pay, which means there's a financial cost. And, I have a limited budget, as you can imagine, to pay. So it takes time. So in the experiment we have here, I would say the system was set up to look more like Twitter than like either Facebook or Telegram. The good news is the dot post framework can be set up to look like anything we want. And it can even look different from Twitter. So imagine Twitter with some interventions that they don't currently do, for example. Because we control the dot post platform entirely, we could pretend it's Twitter with some modification to the way they behave, or we could make it look like Facebook. So if we had made it look like Facebook, we'd probably have replaced the follows with a friend relationship, which is more bidirectional. In Telegram, we'd have to figure out how in the platform we could create closed groups where people can engage in different ways. So you're right, and effectively we can do a lot more, but we've not done it yet.
Okay, dear colleagues, do we have any other questions? Okay, and then I have one more last question about actually what we have already discussed several months ago with you about how to actually stop that influence from bots in Ukrainian context, maybe. Should we, that we already have the experience of banning the entire social network, which was VK, the Russian social media. So my question is, should we do the same as a country to Telegram, for example, which is now where we observe some evidence of FSB roots and some Russian roots in that social media, or according to your study, bots are not a huge problem. Or maybe there is any other ways.
I would say that first of all, many of you on the call would be much bigger experts on social influence operations in Ukraine than me, because I have not studied social influence operations specifically targeting Ukraine. Of course, I'm aware that they are there. We have an ongoing study looking at some deepfakes in Telegram in the Ukrainian context, but what you're looking for, Dimitro, is a much broader study. What I'm seeing is that, Ukraine has been incredibly innovative in many directions in the context of this conflict. And, the kind of thing where at some level, the implications of our paper are twofold. You could use this paper to run influence operations within Russia, and on the other hand, you could use this paper to inform your own defenses against Russian influence operations, which might be coming at you, and enable your bot detection teams to use things like the findings shown through the statistical results that I presented that came out of our experiments. So those are the two ways. I think for me to broadly say you should block Telegram as you've blocked Ukraine in your country, I think that's a call for your defense experts to make because they are better informed about it than me.
Okay, thank you. Dear colleagues, any other questions? Let me check the comments. Okay, we don't have any other questions. So I want to thank you for your time, for your experience, for your extremely relevant report in the context of Russian invasion of Ukraine. So thanks a lot. It was V.S. Subrahmanian, professor from Northwestern University.
Again, thank you for inviting me, Dimitro, and thanks to the audience for their participation by attending, by responding to the questions we asked, and through the questions they asked. And again, my best wishes to all of you in Ukraine. Slava Ukraine.
Героям слава. Thank you.
Bye.